Every physicist knows you should not run in rain, but you still do, because you have been thinking about rain wrong your entire life. Here is what happens. The sky opens up. You are 100 meters from shelter, about 328 feet. Your brain does a quick calculation. Less time in the rain equals less wet. So you run. And you feel clever. You feel like you just outsmarted nature. But here's the thing. There is a wall of water between you and that door. Millions of drops hanging in the air, suspended in the space you have to cross. And whether you walk or sprint, your body sweeps through the exact same volume of space. You collide with the exact same number of drops. Your speed does not change the wall. Only your geometry does. Nature does not care about your common sense. Nature is imaginative. She is subtle. And she has set up a trap for you. Today I want to take you on a journey. We are going to look at something as mundane as getting wet in a rainstorm and find hidden inside it 5 layers of physics, from Newton to quantum reality. And by the end, you will never look at rain the same way again. Let me show you. Now, if you watched our last video on the Fermi paradox, you saw how one simple question, where is everybody, cracked open an entire universe of physics. Today, we are doing the same thing. But instead of looking up at the stars, we are looking up at the clouds. Here is the roadmap. We are going to explore 3 things. First, geometry. How the shape of your body changes everything about how rain hits you, not your speed, your shape. Second, time. Why spending less time in the rain does not mean you get less wet. That one is going to hurt. And third, why running might actually be the worst decision you can make. This is not just physics. This is how the world works. Let us start with what your brain already believes. Rain falls straight down. It lands on your head. The longer you stand there, the more drops hit you. So the solution is obvious. Run. Minimize time. Get to shelter fast. And here's the thing. That logic is not wrong. It is just incomplete. Think about it like this. Imagine you are standing in a room and someone is dropping blue marbles from the ceiling. 1 marble per second. Perfectly vertical. If you stand there for 10 seconds, you collect 10 marbles on top of your head. If you stand there for 5 seconds, you collect 5. Run through the room in 2 seconds. Only 2 marbles. That is the vertical component, and it is real. Franco Bocci's 2012 paper in the European Journal of Physics confirmed it. Vertical rain exposure is directly proportional to time. Spend half the time, get half the drops on your head. So far, so good. Your instinct is validated. But your instinct only sees half the picture, because there is another component, a horizontal one. And that is where everything falls apart. So what is this horizontal component? Here is the problem with how you have been thinking about rain. You imagined yourself as a line, a vertical stick standing in a field. Rain falls on top, you move faster, fewer drops land on you. But you are not a line. You are a 3-dimensional object moving through space. You have a head. You have a chest. You have a face. And the moment you start moving forward, every single one of those surfaces becomes a target. Think about it this way. Imagine a long hallway, about 100 meters, roughly 328 feet. Now freeze time. Every raindrop in that hallway is locked in place. Millions of tiny blue marbles hovering in the air, perfectly still. Now unfreeze yourself. You start walking through that hallway. And as you move, Your body sweeps through that frozen field of drops. Your chest hits them. Your face hits them. Your arms, your legs, everything on your front side collides with those suspended marbles. And here is the critical insight. It does not matter how fast you walk or how fast you run. The hallway is the same length. The volume of space your body passes through is the same. You hit the exact same number of drops on your front. Your speed changes nothing about the wall. You are a snowplow, and the snow is already there, waiting. Remember Neo dodging bullets in The Matrix? He did not speed up. He changed his cross-section. He changed his geometry. That is the physics. And this is where it gets beautiful. Because once you understand that the horizontal component depends on your cross-section, on the shape you present to the rain, the question changes completely. The question is no longer, how fast should I run? The question is, what shape should I be? Picture two runners. Runner A stands upright, chest out, full frontal area exposed, about 0.5 square meters, or roughly 5.4 square feet, of surface facing forward. Runner B leans forward, arms tucked in, head down, like Superman in flight. That frontal area drops to maybe 0.3 square meters, about 3.2 square feet, a 40% reduction. Same speed, same distance, same rain. But Runner B presents a smaller target. Runner B sweeps through less volume. Runner B gets less wet. The answer is not just run. The answer is change your geometry. And if that sounds familiar, it should. In electromagnetism, the energy a surface absorbs depends on the angle of incidence. The angle between the incoming wave and the surface it hits. Tilt a solar panel and the output changes. Tilt your body in rain and the physics is identical. You are not dodging rain. You are optimizing your angle of incidence. You are doing physics. You just did not know it. So now we have a fight. Between the top of your head and the front of your chest. Think about what we just found. The top of your head wants you to run. Now faster means less time, fewer vertical drops. That is real. But the front of your chest says it does not matter. You hit the same wall no matter what. That is also real. Two parts of the same body. Two opposite answers. One wants speed. The other wants geometry. Who wins? To find out, we have to go back. To the giants of the past. Think of Galileo. Think of Newton. These are the people who looked at a messy, confusing universe and said, "Let me chop it into pieces." That is the secret to classical physics. You cannot solve a complicated problem all at once. You have to decompose it. Break it down into components. Handle each piece separately. So let us do exactly that with our rain problem. A raindrop has a velocity. That is just a fancy word for an arrow pointing straight down. When you stand still, every drop falls vertically onto your head. Simple. But the moment you start running, something shifts. You now have your own arrow, pointing forward. And because you are the observer, from your perspective, the rain's arrow tilts. It is no longer straight down. It is coming at you from an angle. You have felt this. Think about driving in a rainstorm. At 30 kilometers per hour, about 19 miles per hour, rain hits the windshield at a gentle angle. At 100 kilometers per hour, roughly 62 miles per hour, rain smashes nearly horizontal into the glass. The roof stays almost dry. The windshield takes the full impact. The faster you move, the more horizontal the rain becomes relative to you. That is relative velocity. Newton figured this out centuries ago. So here is Newton's triumph. We can now calculate the total wetness as the sum of exactly two things. First, the wetness from above. This depends on time. The longer you stand in the rain, the more drops land on your head and shoulders. You already know this from the blue marbles. Second, the wetness from the front. This depends on distance. Remember the frozen hallway? That wall of suspended drops between you and shelter. It is fixed. If the nearest door is 100 meters away, about 328 feet, the amount of water waiting in front of your face is locked in. You cannot change it. It is a wall of water, and you have to walk through it no matter what. So the vertical cost depends on time. The horizontal cost depends on distance, and the distance to shelter is fixed. That means there is only one variable you can control: time. And Newton's calculation says, run. Run as fast as you possibly can. Minimize the time. The distance cost is already paid. The wall is already built. You cannot shrink it, but you can spend less time under the vertical rain. And there it is. A clean, complete answer from classical physics. Case closed. Except, it is not closed. Because if Newton's answer were the whole story, why does it feel so wrong? Why? When you sprint through a heavy downpour, do you feel like you are getting absolutely soaked to the bone in seconds? And we have not even mentioned wind. In the real world, wind can push rain sideways, completely reshaping the geometry of the problem. A strong headwind turns gentle vertical rain into a horizontal assault. A tailwind might actually shield your front. There is a crack in our beautiful model. We are treating you like a simple geometric point, but you are not a point. You are a complex, three-dimensional shape moving through a fluid that splashes, bounces, and swirls. And even if we stay in the ideal world of physics, no wind, no splash, no turbulence, there is something deeper. Something that connects this simple rain problem to how we understand atoms, how we understand light, how we understand the universe itself. But before we dive into that deeper layer, let us pause. Because so far, everything we have discussed is theory, elegant theory. Newton's vectors, the frozen hallway, cross-sections and geometry, all beautiful on paper. But does it actually hold up in the real world? It turns out, actual scientists asked this exact question, and they tested it. In 2012, Italian physicist Franco Bocci published a paper in the European Journal of Physics titled, and I am not making this up, Whether or Not to Run in the Rain. Yes, a peer-reviewed paper about rain. Bocci built a mathematical model that accounted for body geometry, not just a point, but a real three-dimensional human shape. Head, shoulders, chest, back, legs. He calculated the optimal speed for different body types, different rain intensities, different distances. His conclusion: running does reduce total wetness. Newton was right about that. But here is the twist. The benefit has diminishing returns. Past about 3 meters per second, roughly 10 feet per second. A moderate jog, the marginal gain from running faster drops dramatically. And if the wind is blowing from behind you, running can actually make you wetter, because you are effectively chasing the rain, sweeping your front through drops that would have passed ahead of you. And Bocci was not the only one. The television show MythBusters ran a controlled experiment. 2 hosts, identical clothes, same 100-meter stretch, about 328 feet. One walked, one ran. The results? The runner absorbed roughly 40% less water on top, the head and shoulders. Significant. But the difference on the front of the body, the chest, the face, the legs, Chinti Tren Man UNH, front body wetness difference, 0%, nearly zero. The horizontal wall is real. It is not just a thought experiment. It is not just blue marbles in a frozen hallway. It is measured, tested, published science. Physics does not care about your intuition. So the experiments confirm what Newton predicted, with a twist. Running helps your head. It barely touches your front. And the geometry of your body matters more than your speed. But there is still a flaw in our model. A crack in the logic that goes deeper than Newton ever imagined. So what is this flaw? Here is the problem. Newton's model treats rain like a math problem. Vectors on a chalkboard. Neat little arrows pointing in neat little directions. And it works beautifully for a simplified world. But you do not live in a simplified world. You live in a world where you are not a point. You are not an arrow. You are a complex, three-dimensional shape hurtling through a field of projectiles. And that word, projectiles, is important. Because the moment you start thinking of raindrops as projectiles and your body as a target, you have just stepped into one of the most powerful ideas in all of physics. Cross-section. In particle physics, cross-section is everything. When physicists at CERN fire protons at each other at nearly the speed of light, they do not ask, will they hit? They ask, what is the cross-section? How big is the target? How likely is the collision? Think about it like this. Imagine you are standing in a field. Someone is firing tennis balls at you from every direction. How many balls hit you depends on exactly two things. 1. How big a target you present. Stand facing the shooter with your arms spread wide. Maximum hits. Turn sideways, tuck your arms in. Fewer hits. Same number of balls. Same speed. Same distance. But your cross-section changed. 2. How much space you move through. Walk 10 meters through that field of tennis balls, and you sweep through a certain volume. Walk 100 meters. You sweep through 10 times more. And here is where it crystallizes into something beautiful. The total volume your body sweeps through is given by one elegant equation. Volume equals area times distance. A is your cross-sectional area, the shadow your body casts in the direction you are moving. D is the distance you travel. Look at that equation. Really look at it. Time is not in that equation. Speed is not in that equation. The number of horizontal raindrops you collide with depends only on your shape and how far you travel. Not how fast. Not how slow. The wall of water does not care about your urgency. And this is exactly how particle physicists calculate collision rates. The number of interactions equals the cross-section times the flux, the density of particles flowing through a given area. Replace protons with raindrops and accelerator beam with rainstorm, and the physics is identical. Feynman knew this. He spent his career calculating cross-sections for electrons, for photons, for quarks. And when he walked in the rain, he saw the same physics everywhere. The universe does not have separate rules for the small and the large. It has one set of rules, and rain obeys them. So let us step back and see how far we have come. Because we started with a question a 5-year-old could ask, and we have arrived somewhere extraordinary. Layer 1. Common sense. Run, minimize time. Simple. Layer 2. Newton. Decompose into vertical and horizontal. Elegant. Layer 3. Cross-section. Your shape matters more than your speed. The formula V equals A times D has no time variable. Powerful. 3 layers deep. each one revealing something the last one hid. But we are not done. Because there is a fourth layer, and it changes everything. That fourth layer? Time. Not time like how many seconds you spend in the rain. We already covered that. Newton covered that. I am talking about something deeper, something that changes the entire framework. In my lectures, I often talk about space-time, not space and time, as if they are two separate things you can handle independently. Space-time. One word, one thing, a four-dimensional fabric that everything in the universe moves through. And here is where it gets strange. Because when you add time as a real physical dimension, not just a clock ticking in the background, but an actual axis you move through, the rain problem transforms into something completely different. Let me show you what I mean. Imagine a sausage, a big, long salami. Stay with me. Now slice that sausage straight across, perpendicular to the length. You get a perfect circle. That circle is a snapshot of now. Everything happening at one instant. The rain, your body, the air between you and shelter, all frozen in one slice of time. Now slice at an angle. You get an oval, a different shape, a different perspective on the same sausage. Same sausage, same meat. But the shape you see depends entirely on how you cut it. On the angle of the knife. That sausage is space-time. The length is time. The width is space. And the angle of your slice? That is your velocity. Now here is where it gets powerful. When you stand still in the rain, your path through space-time is a vertical line, straight up through time. You sit at one fixed point in space while time marches forward. Raindrops have their own lines, slanting diagonally through space as they fall while time moves forward. Every point where your world line crosses a raindrop's world line, that is a collision. That is you getting wet. Each intersection is a splash on your skin. Now start running. Your world line tilts. It is no longer vertical. It slants through space-time at an angle. And here is the insight that unifies everything we have learned so far. When your world line tilts, two things happen simultaneously. First, you cross fewer vertical raindrop lines. You spend less time under the rain. Newton was right about this part. Second, you cross more horizontal raindrop lines. Your tilted path sweeps through more space per unit time. The cross-section formula was right about this part too. But now, for the first time, you can see both effects at once. In one picture, one diagram. The total number of intersection points, the total wetness, is determined entirely by the geometry of your path through four-dimensional space-time. This is not just rain anymore. This is special relativity in a rainstorm. The same mathematics that Einstein used to prove that moving clocks run slow and moving rulers shrink, that exact framework, applies to you running through rain. The geometry of space-time does not care whether you are an astronaut approaching the speed of light or a person sprinting to a bus stop in a parking lot. The rules are identical, only the scale is different. And that sausage analogy? It is not just a teaching trick. Physicists actually use this concept. They call it a worldtube, the four-dimensional volume your body occupies as it moves through space-time. Your total wetness? It is literally the number of raindrop world lines that penetrate your worldtube. So rain is relativity. Relativity is rain. The mundane and the cosmic, same physics. But we have been playing it safe. We have been talking about running at human speeds. 3 meters per second, about 10 feet per second. Maybe 10 at a full sprint. What happens when we stop being safe? What if rain did not fall at 9 meters per second, about 30 feet per second, the gentle speed of a normal raindrop. What if it fell at the speed of light? Think about what that means. At the speed of light, time dilation becomes infinite. From the raindrop's perspective, it experiences zero time falling. It leaves the cloud and hits your head in the same instant. No journey, no arc through the air, no gentle descent. Just a departure and arrival. Simultaneous. The raindrop does not experience falling. For the raindrop, the cloud and your skull are the same location. Now flip to your point of view. Standing on the ground, looking up. Every raindrop that will ever hit you during your entire walk, every single one, from the first step to the last, arrives at the same instant. All of them. Simultaneously. The entire future of your wetness, compressed into one catastrophic moment. Not a rainstorm, an event. And it gets worse. A single raindrop weighs about 0.05 grams, roughly the weight of a small grain of rice. Now apply Einstein's most famous equation. The mass-energy equivalence of a single raindrop is about 4.5 billion joules, roughly 1 ton of TNT per raindrop. One raindrop. 1 ton of TNT. And a typical rainstorm drops about 100 million droplets per square kilometer per second. That is what happens when you take rain, the most mundane, boring, everyday phenomenon on Earth, and hand it to Einstein. The mundane becomes terrifying. The familiar becomes alien. And the question, should I run in rain, becomes, how does the universe allow me to exist at all? But we are not done, because there is one more layer. And this one does not just change how you calculate rain. It changes whether rain exists at all. Layer 5. Quantum mechanics. Up until now, every layer we explored assumed one thing, that a raindrop is a thing, a solid, definite, such a real object, flying through the air with a definite position, a definite velocity, a definite trajectory. Quantum mechanics says, not so fast. Here is what Feynman knew better than almost anyone alive. At the most fundamental level, a raindrop is not a single object with a single path. It is a collection of roughly 10 to the power of 21 water molecules. That is a 1 followed by 21 zeros, each one governed by quantum mechanics. And in quantum mechanics, nothing has a definite position until it is measured. Nothing has a definite trajectory until it interacts with something else. You have probably heard of the double-slit experiment. Fire a single electron at a barrier with 2 slits. Common sense says it goes through one slit or the other. Quantum mechanics says it goes through both simultaneously. And on the other side, it creates an interference pattern, a wave pattern, that proves it was in 2 places at once. Now here is the question that should keep you up at night. Not, does a raindrop do the same thing? At the scale of a single water molecule, absolutely yes. Every water molecule in that raindrop exists as a probability cloud. Not here or there, here and there. A smear of possible positions, weighted by probabilities, described by something called a wave function. But here is where Feynman's genius comes in. He did not just accept quantum mechanics. He reimagined it. Feynman invented something called the path integral formulation. And the core idea is breathtaking. Instead of saying a particle goes from point A to point B along one path, like Newton would say, Feynman said it goes along all paths, every possible path, simultaneously. The straight line, the curved line, the zigzag, the loop, the path that goes to the edge of the universe and back. All of them. And the probability of arriving at point B? It is the sum of contributions from every single one of those infinite paths. Most cancel out. Some add up. And what survives, what you actually observe, is the classical trajectory. The path Newton predicted. So when a raindrop falls from a cloud to your head, Feynman would say it does not take one path. It takes every path. The raindrop that hits your skull is the sum total of an infinite number of quantum histories, most of which you never see. Think about what that means for our rain problem. We spent this entire video asking, how many raindrops hit you? Newton said, decompose it. The cross-section formula said, V equals A times D. Spacetime said, count the intersection points in your worldtube. But Feynman would ask a deeper question. He would ask, what is a raindrop? Is it a particle with a position? Or is it a wave of probability that only becomes a particle when it touches your skin? Because if rain is probability, if each drop is a cloud of maybe, then the question, should I run in rain, is not a question about physics. It is a question about reality itself. And that is the fifth layer, hidden inside every rainstorm. So let us see the full picture. 5 layers. Layer 1, common sense, run, minimize time, incomplete. Layer 2, Newton, decompose into vertical and horizontal, elegant, but treats you as a point. Layer 3, cross-section, V equals A times D. Your shape matters more than your speed. No time variable, powerful. Layer 4, space-time, world lines, worldtubes. Rain is relativity, unifying. Layer 5, quantum mechanics. And raindrops take every path. Reality is probability. Feynman's deepest insight. But you are standing at a bus stop. It starts raining. You have 100 meters to go, about 328 feet. What do you actually do? Here is the practical answer, informed by 5 layers of physics. Run. But lean forward, tuck your arms, minimize your cross-section, and if the wind is at your back, slow down. Let the rain pass ahead of you. That is the answer Newton gives. That is the answer Bocci's experiments confirm. That is the answer the cross-section formula predicts. But Feynman would add one more thing. He would say, while you are running, look up. Watch the drops fall. Because hidden inside that ordinary moment is geometry and flux and space-time and quantum probability. The entire universe performing for you, for free. That is why Feynman stopped running. Not because it was optimal, but because he wanted to see the show. So let us bring this all together. We started with a question. Should you run in rain? And the answer led us somewhere no one expected. 5 layers deep. From common sense to quantum mechanics. From blue marbles falling on your head to Feynman's path integrals, where every raindrop takes every possible path through the universe simultaneously. And here is what I want you to take away. The wall of water is real. It is always there. Between you and shelter, between you and wherever you are going, and millions of drops suspended in the space you have to cross. And your speed does not change that wall. Only your geometry does. Newton said, run. And he was right. For the top of your head. Bocci proved it in 2012. MythBusters confirmed it on television. Running reduces vertical exposure. That is measured science. But the front of your body, the chest, the face, the legs, the cross-section formula says V equals A times D. No time variable. No speed variable. The wall does not care how fast you move through it. And when we lifted this simple problem into space-time, into world lines and worldtubes, we saw both effects at once. for the first time. In one picture. Rain is relativity. Relativity is rain. And when we handed the problem to quantum mechanics, even the raindrops themselves dissolved into probability. Clouds of maybe. Taking every path. Feynman's deepest insight. Applied to the most ordinary moment in your life. That is what physics does. It takes the mundane and reveals the extraordinary hiding inside. Nature set a trap for you, not to trick you, but to teach you, if you are willing to look. And now you will never look at rain the same way again. So the next time the sky opens up and your instinct says run, go ahead. Run. Lean forward. Tuck your arms. Optimize your cross-section. But maybe, just maybe, slow down for a second. Look up. Watch the drops fall. Because hidden inside that ordinary moment is geometry and flux and spacetime and quantum probability. The entire universe, performing for you, for free. If this changed how you see something as simple as rain, let me know in the comments. What layer surprised you the most? The wall of water? The cross-section formula? The light-speed raindrop? Subscribe if you want more physics explained the way Feynman would have explained it. No memorization, just understanding. And I will see you in the next one.